Hello everyone, and thank you for joining us for today's webinar. We're just going to wait a few minutes just to let the last few attendees join, just so that they don't miss out on the beginning. In the meantime, please do take a moment to familiarize yourself with the GoToWebinar panel, just so you know how to submit questions and engage in the session. Thank you. Hello everyone, and thank you for joining us for today's Surface Measurement Systems live webinar. The title of today's session is Moisture Content and Pharmaceutical Ingredients. Now, before we start for today, I just wanted to note a few rules for the session. We will have a live Q&A and at the end of the session with Mei-Shan Gao. So if you would like to engage in this, there are two ways you can do so. You can submit a question in the questions panel in writing, and then I will submit that question myself to Mei-Shan at the end of the session on your behalf. Or if you have a maybe slightly more expansive question or a question you would like to ask to Mei-Shan yourself, then please, by all means, put your hand up, raise your hand, and then I will let you know when you can unmute your microphone so you can ask the question over the mic. Just to remind everyone, you will be muted for the duration of the presentation, just so that there's no background noise or feedback disrupting the audio quality of the session. Today's speaker is Mei-Shan Gao, an application engineer here at Surface Measurement Systems. Since joining us in 2018, she's been working on surface characterization of solid materials, including fiber, powder, and film samples. She specializes in the techniques of dynamic vapor absorption and inverse gas chromatography. Mei-Shan obtained her master's degree in chemical engineering at Imperial College London in December 2017. Her research project focused on investigating the properties of fragrance molecules with solid substrates by diffusion and sorption. She obtained her bachelor's degree in chemical technology at the Hong Kong Polytechnic University and in chemistry at Sun Yat-sen University in June 2016. So without further ado, I will hand over now to Mei-Shan to begin her presentation.
Thank you, John, for the introduction. I'm going to share my screen and let me know if you can see it now.
Yes, we can see and hear you, Mei-Shan.
Okay, that's great. So good morning, good afternoon, and good evening, everyone around the world. I'm Mei-Shan, and thank you for joining today's webinar. So our topic today is about the moisture content and the pharmaceutical ingredients. And here I would like to introduce you a really helpful tool to measure the moisture content and the sorption behavior for some pharmaceutical materials, which is a dynamic vapor sorption technique. So here's the outline of the presentation. I will first give a very brief introduction about the background of the DVS, like the instrument or the principle, and then we can go through different methods we can perform with the DVS technique, and followed by some applications related to the pharmaceutical industries with some examples of the pharma ingredients. So moisture is everywhere in the real world, and it can cause lots of different problems for different samples. For example, for the powder sample, it could cause like the caking of the powder and affect the flowability of the powder. And also the moisture in the valve on the right hand side, it will like lead to the dissolution of the freeze-dry material, and that will affect the application of the sample. So it's quite important to study the moisture sorption behavior of those kind of pharmaceutical products, and DVS could be a really useful tool to modulate or simulate the conditions for the storage of the material or during the application. So DVS is short for the dynamic vapor sorption, which is basically a gravimetric method that we can measure the mass change of the sample at different concentrations of moisture or organic vapors. So it's based on a really accurate balance with the resolution of 0.1 microgram. So we just need to use very small amount of sample for the analysis, and typically just around 10 to 20 milligram. And there will be a continuous flow of the pro-molecule to the sample all the time, so we can achieve a much faster equilibrium compared to the static method. And the whole sorption-desorption experiment can be finished within a few days, like 2 or 3 days, up to different sample amount. And for the conditions, we can perform the experiment at ambient temperature and pressure, which keeps the original nature of the sample without any damage. And this is quite important, especially for some fragile material, like the pharmaceutical material with any hydration water. We don't need to dry out the water during the measurement in some other method. For example, the volumetric technique at low condition, it will dry out the sample. And in that case, the nature of the sample already changed. And for the DVS method, we can get the property much related to the real world condition when we apply the sample or doing the product. So the principle of the experiment is very simple. We have a macro balance in the system connect to both the sample pan and the reference pan. And there will be carrier gas for the system, either for nitrogen or dry air. And as you can see at the back of the system, there are 2 reservoirs. So on the left-hand side is for water, and the other side is for the organic vapor. So the mass flow controller inside the system will control the flow of the carrier gas and the saturated vapor in ratio to get a certain level of relative humidity or partial pressure. And then the sensor in the lines here will detect the concentration of this mixture and see whether see if this moisture or the concentration is reaching the target value. And then this mixture will flow to both the sample chamber and the reference chamber at a constant rate. And the sample inside this chamber here will pick up the moisture, and the mass change will be recorded by the balance. And the whole stand, like this one, will be set in an incubator with the temperature range from 5 to 85 degrees. That means we can perform the experiment with the whole range of the temperature from 5 to 85. And in case some of the sample, if you want to precondition the sample at higher temperature to remove the moisture beforehand, we also have an in situ preheater that allow you to put the preheater inside the system, and you can precondition the sample up to 200 degrees before the experiment. And some other accessory can be also integrated with the system. For example, at the same location as the preheater, we can also install a video camera that take the sample image at the end of each step, or you take the sample image at a fixed interval of time. And in that case, you can have a good or a very clear view about the sample changing in the nature or changing in different forms. So for example, here is an example of the freeze-dried material. And as you can see, at certain point of humidity, which has the legend here on the right-hand side, and the sample just collapse, shrink, and then go to the liquid form. So we can get the critical condition of the humidity as well as the temperature for the storage of this freeze-drying material. And another accessory can be integrated with the system is the Raman spectroscopy. So inside the DVS chamber, we have a port for the Raman gun, and we can take the Raman spectra at the end of each humidity step. So on the left-hand side, here's an example with the amorphous lactose sample at 25 degrees. And on the left-hand side, we have the DVS data for the moisture sorption, that we change the humidity, which is the blue line here on the right hand. So the humidity changing from 0 to 90 or 95% RH with 10% intervals. And the right line is the change of mass for the sample. So the sample is losing the mass at the very beginning, just the flow of the carrier gas for drying. And then it starts picking up the moisture and then reach an equilibrium. Then it will jump to the next stage automatically. And at 60% RH here, you may notice that the mass is decreasing a lot, and this is due to the amorphous to the crystalline phase change. And this phase change doesn't happen in the second cycle, so it's a kind of irreversible crystallization of the material. And these are some information we can get just from the DVS data. And we also collected the Raman spectra at the end of each stage, and at 0 and 40% RH, this Raman spectra shows an amorphous form of the material. And exactly above 60% RH here, there are some new peaks showing up here. And these new peaks just indicating of the crystalline state of the material. And the Raman spectra also confirming with our conclusion in the DVS data that the sample will go through from the amorphous phase to the crystalline phase at 60% RH. And the same as the video image we collected in the bottom of the slide. So for the amorphous state of the material and the crystalline state of the material. So the combination of three techniques here just give us a really great understanding about the solid characterization for different materials. So that's basically the information about the system we have and the technique we are using. And now we are going to introduce some typical method we can perform with the DVS technique. So the first method is a very simple one, just the step method. This step method can be applied to either moisture sorption or the organic vapor sorption. So this can be chosen inside the software on the A side for moisture or on the B side for the organic vapor. And how we perform the experiment is the same as we introduced previously. So the blue line is the partial pressure of each step, which has the axle on the right-hand side here, the target relative humidity. So it's changing from 0 to 90% RH with 10% intervals, and from 0 to 90, and then desorption to 0, and it's a two-cycle experiment, so the first cycle and the second cycle. And the right line is the change of mass for the sample. The drying stage here, just the flow of the carrier gas to the sample to establish the initial dry mass of the material. So that could tell you about the initial moisture content inside the material. And then we can get the equilibrium state at each stage, and those values will give us the equilibrium moisture content of the material at each relative humidity. And as for this sample, as you can see, at 90% RH, the mass of change is around 20%. That means the sample has really good affinity with water. And those water could be either on the surface, or it can also go to the bulk of the material. And during the second cycle here, the moisture sorption at 90% RH is almost the same level of the first cycle. That means it's a totally reversible process. So it can go back to the same level in the second cycle. And these are the moisture sorption kinetics data from a mass plot, which is a mass change as a function of time. And if we take the equilibrium mass uptake and plotting against the target relative humidity, then we can get this moisture sorption isotherm for the experiment. So we have the red line for the sorption branch and the blue line for the desorption branch. And there are quite a lot of information could be get from this isotherm plot. So the same at 90% RH, 20% change in the mass, and which means this sample is going through a bulk sorption dominated mechanism compared to some surface sorption of the low uptake sample. And the desorption is going back to 0, means a perfectly reversible process. And as you can see, there are a little gap between sorption and the desorption, and this is called the hysteresis gap. And this is because when the molecules during the desorption process is from the bulk to the surface, and it's a diffusion limited process, it will give some different kinetics compared to the sorption branch. And this will cause the hysteresis between sorption and desorption. So for example, if there is more energy input, like higher temperature, if you perform the same experiment, there will be more energy for the water molecule for diffusion. Then you will be expecting a smaller or narrow hysteresis gap compared to 25 degrees, this one. I do have an example later with the macrocrystalline cellulose that I can show you how the temperature will affect the hysteresis gap. And for this isotherm, it's a quite typical type 2 isotherm, which indicates like it's beginning with a monolayer region, and then the multiple layer region with lessly bound water, and then at higher humidity has the free water. And for the monolayer region, it's a very stable state, and that could be related to the stability of the pharmaceutical ingredients. And for the step method, the first example I'd like to show you is about the potassium citrate. So we performed the same moisture sorption experiment with a full cycle of sorption and desorption from 0 to 95% RH with 10% intervals. And we only use around 8 milligrams of the sample for the analysis because the sample can pick up quite a lot of water with the dissolution at higher humidity RH. So here we have the mass plot of the experiment. And as you can see, the sample is pretty stable below 60% RH. There is almost no uptake at all. And from 60 to 70% RH, it begins to pick up lots of water. And at 95% RH here, the mass change could reach almost 200%, and it's still not quite equilibrium yet, and which is just basically the condensation of the water droplet on the sample pan. And at the end of the desorption during the first cycle here, and you can see it's not going back to 0. So that means this moisture sorption and desorption is an irreversible process. So the final sample is different from the original sample at the very beginning, with some water molecules still trapped inside of the material. And then we can plot the isotherm with the analysis software, basically just taking the equilibrium mass and plotting against the target partial pressure or relative humidity. And then we can get this water isotherm for the experiment. And this report just giving you the equilibrium mass change at different humidity steps, and as well as the hysteresis between the sorption and desorption. So on the left-hand side is the corresponding moisture isotherm, and from the isotherm, it shows a large increase of the water sorption capacity at 70% RH, as well as 90% RH stage, which is an indicative of a transition step, and the large increase in the water sorption capacity at certain RH step can be also indicative of a hydrate formation, and the shape of this resulting hysteresis is quite typical for the formation of the hydrate. And some other information we can see here also like an open loop isotherm, which means an irreversible process. So this is just the isotherm, and we also take the photo image at each percentage RH step, and we can compare from the photo image that you can see from 0 to 60% RH, the sample basically just keep the same original nature of the sample up to 60% RH. And then when the humidity keeps increasing above 60, it starts dissolving. And then the sample is fully dissolved at 95% RH. During the desorption step, it keeps at liquid form up to until 40% RH. And then at 30% RH, there is a sudden crystallization of the material. Then the mass change of the sample doesn't change anymore between 0 and 30%. And at the end of the desorption step is a kind of crystalline form as well, rather than the particle form at the very beginning during the sorption step. So we can easily study this kind of morphology changes with the humidity, with the combination of the DBS and the video function. And it can give a really good idea about how the morphology will change along with the different humidity. So that's the example about the potassium citrate. We also have an example with the macrocrystalline cellulose, and this time we would like to study the temperature effect on the moisture content of this macrocrystalline cellulose sample. So we use around 10 to 20 milligram of MCC sample, and we perform the same water sorption experiment from 0 to 95% RH at different temperature, so from 5 to 60 degrees. And here are the results for all the temperature. So different color for different temperature. Between 5 and 25 degrees, the moisture uptake at a particular relative humidity doesn't show a significant difference, but the time to reach the equilibrium is much longer. And then from 40 to 60 degrees, this result shows the increase in temperature, the moisture sorption capacity decreased a lot, and which is probably due to a structural rearrangement. And during the higher temperature, the sorption kinetics keeps increasing with the elevated temperature as well. And the experiment time for 60 degrees, which is the gray line here, is around 3 times faster compared to 5-degree run for this macrocrystalline cellulose sample. So temperature has a really great impact on the kinetics of the material and also affecting the sorption capacity at higher temperature. So from these data, we can also calculate the diffusion constant for the water molecules at different temperatures. And the diffusion constant is calculated with the average particle size of the microcellulose material, which is about 50 micrometer. And this diffusion constant also shows the trend of increasing with the increasing temperature. And another observation is about the hysteresis gap between the sorption and desorption isotherm. So the right line is for the 25-degree run, the blue line is for the 50-degree run, and the green line is for the 60-degree run. So as the temperature increases, the water molecules move more freely out of the box structure, and that will result in a smaller hysteresis gap and an increase in the diffusion constant in the previous slide as well. So there are more energy input, and this will result in the smaller hysteresis gap. So this simple study just demonstrates the effect of the temperature on the moisture sorption kinetics at a range of relative humidity conditions within the temperature stability of the material. And we recently released the technical note related to this study. So if you're interested, we are happy to share the note with you after the webinar. And all the previous study is about the step method. The other method we normally perform with DVS technique is the ramping method, which is a quicker and easier way to measure the stability of the solid material. And it's very similar to the DSC temperature ramp. So in case of the DVS, we ramp the humidity from 0 to 90% RH at a constant rate. And here's the result for the lactose sample. And it's quite clear that this lactose is first losing the mass because of the drying stage. And then the water sorption begins very slowly because of the surface sorption at the very beginning here. And after a certain point of humidity, the mass increase will become dramatically changing here because the water is not just on the surface, but also penetrate the surface and go to the bulk of the material. So by comparing the slope before and after this change, we can get this point for the glass transition, and we can easily detect the glass transition humidity for this sample at 25 degrees. And as the humidity keeps increasing, the sample will also go through the crystallization step that the mass change will decrease dramatically. This is because the crystalline state has smaller surface area as well as less sorption capacity. So from this single plot, we can easily determine 2 points. So one point for the humidity for glass transition, and another point for the humidity for the crystallization of the material. And this is the experiment performed at one single temperature, 25 degrees. And we can also perform the same ramping experiment at different temperatures. And at each temperature, we can get 2 points, glass transition point and crystallization point. Then we can plot this stability mapping of the material at a series of different temperatures. So if we have a combination of the condition we want to store this sample, for example, a combination of the temperature and humidity, we can easily predict the sample is at a stable amorphous state or an unstable state or the crystalline state of the material. So this stability mapping is quite important for the storage or the application of the pharmaceutical ingredients. And one of the examples I have here is about the impact of the protein concentration on the vapor induced crystallization or the phase transition of the material. So normally we have the amorphous sugar sample, and they are always mixed with some protein sample to increase the stability by any kind of method like freeze drying method or spray drying method. And it's very important to study the moisture sorption behavior of this mixture and see what's the impact of this protein on the stability of the mixtures. So the study we have here, we have the bovine serum albumin protein, and we also have the sucrose sample. And we want to mix the two samples to improve the stability of the sucrose sample. So we have the mixtures in different ratios, and we perform the water sorption experiment, the ramping method as we introduced previously on all of the sample here. So the experiment are performed at 25 degrees, and here's the result. The red line is for the pure sucrose sample, and the black line is for the pure protein sample, and the other line just for the other the mixtures in different ratios. And what we can observe here is all the sucrose containing sample has a glass transition point around 23% RH. And this value is quite consistent with the literature value for the pure sucrose sample, which is around 23% RH at around 25 to 30 degrees. And with different loading of concentration of the protein, as you can see, the glass transition has very little impact for the loading of concentration. The lines are just overlapping here. So protein has very little information or impact on the glass transition. As for the crystallization, so the pure sucrose sample can crystallize at around 50% RH. And with the increasing of the protein concentration, this crystallization point is shifting to higher humidity, which means this protein can behave as a stabilizer to stabilize the mixture from the crystallization with the humidity. And this is probably because of the protein-sugar interaction could delay the sugar crystal nucleation, and that will result in the inhibited crystallization. So here we can see the BSA protein is a really good stabilizer for the protein-sugar formulation with the interaction between the protein and the sugars. And DVS here could demonstrate or mirror this kind of influence for the protein concentration and the stability about the vapor-induced phase change. And the next application related to pharmaceutical is the determination of the amorphous content. And we do have quite a lot of different methods for the amorphous content determination. And here I just want to introduce one of very unique method we always apply, which is based on the crystallization point and the fact that the sample will squeeze out any kind of adsorbed molecules before and after the crystallization. So we just mirror the uptake before and after crystallization point. And for this method, we first need to have a sample of interest that will be induced the crystallization by a vapor. So for example, one of the sample we have, and we perform the acetone sorption on the sample, and at 60% RH, it will crystallize the material. There is a significant decrease in the mass. And when we set up the method, we just simply set different stages. So first we expose the sample before the crystallization point about 30% RH for both the amorphous and the crystalline material. And then we expose the sample above the crystallization point, so about 85% RH for crystallize all the amorphous content inside the material. And the third stage, we just expose the sample again to 30% RH for the fully crystalline material this time. And as you can see, there is a difference between the first and the last stage 30% RH step. And this difference in the mass is because of the amorphous content of the material. And we have a standard material for the calculation as a reference, and be percentage to that standard material, we can then calculate what's the amorphous content of the sample of interest. So the example I have here is the fluticasone propionate sample, and we have this sample of unknown amorphous content, and we do have 3 other standard of the same nature, which is 2% amorphous, 5% amorphous, and 100% crystalline material. And to start the experiment, we first need to measure all the standard sample with the same method as we introduced previously. So we use ethanol as a crystallization solvent for the sample. We perform the experiment at 25 degrees with around 50 to 100 milligrams of the sample. So it's first beginning with some drying stage in the middle, and there are 2 important stages. Is 20% RH before the crystallization point, and we comparing between the 2 20% RH step for the mass change of the material. So here's the result for the experiment. The right line is the sample of interest, is the amorphous sample with unknown amorphous content, and the green line and the pink line is the standard material, fully crystalline material, and then 2% amorphous content material as the standard. So we have the mass change of this crystalline material or the amorphous standard, and then we have the mass change for the sample of interest. So we have the calibration line from the standard material, and we fit in this point in the line, then we can get the amorphous content of the material of interest. So it's quite simple experiment as long as we can find a solvent that will induce the crystallization and a standard of the same nature of the material. So some of the advantage and the disadvantage of this method. So this method is quite accurate, especially for some low amorphous content material compared to some traditional method. We can get a really good reproducible and accurate method with this pre and post amorphous content crystallization method, and we can detect as low as 0.2% amorphous content inside the material. And some of the disadvantage is for this method, we first need to have a standard with no amorphous content as a reference value, and then we also need to find a vapor that will induce the crystallization inside the material. And we do have some other methods, so if you're interested in the amorphous content determination, you are more than welcome to contact us, and we can introduce the other method for you as well. And the next application quite relevant to the pharmaceutical application is the BET surface area determination. And the theory we use here is just exactly the same as volumetric technique with nitrogen sorption. So we can measure the amount of vapor absorbed by the surface and also the vapor pressure above the surface. And then we can fit in the line to get the monolayer volume and the sorption constant. And with the cross-sectional area of the pro molecule we are using, we can then calculate the BET surface area of the material. And this method is quite important that you want to get a type 2 or type 4 isotherm with the monolayer region for the calculation of the BET surface area. And what we normally use is some organic vapors like octane or ethanol as a pro molecule, and you just do the sorption of the pro molecule organic vapors. Then from the points inside the BET range, which is between 0.05 to 0.35, then we can get the BET surface area of the material. So normally the water sorption or moisture sorption is not very recommended to calculate the BT surface area because the water isotherm is usually a type 3 isotherm, which means there are more water-water interaction than the water is forming the cluster on the surface rather than cover the whole surface with monolayer. So first example I have here is with alpha lactose monohydrate that we perform the octane sorption at 25 degrees from 0 to 90 or 100% RH with 5% intervals. But what we use for calculation is basically just between 0.05 to 0.35, only using these points for the calculation. So we have the octane isotherm for the sample, and it's a quite good type 4 isotherm. And then we fit in the lines with the BET equation in the previous slide, and we get this BET plot. And from the slope and the intercept of this plot, we can then calculate the monolayer volume as well as the sorption constant of this material. And with the cross-sectional area of the octane molecule, we can then calculate the BET surface area of this lactose sample is about 0.26 square meter per gram. And this value is quite consistent with the literature reported value for the pharmaceutical grade lactose sample. And as you can see, the R square is quite linear BET plot as well. So for the DVS, we can measure some very low surface area material still with very good reproducibility. And we can also measure some high surface area material. And here just an example with the titanium dioxide. We also perform the octane sorption from 0 to 90% RH with 5% interval in the BET range, and then 10% interval just to get a full isotherm. So we also use the points in the BET range to calculate the surface area, and the same equation as before, we get the monolayer volume and the sorption constant, and the surface area for this TiO2 sample is about 52 square meter per gram with quite linear regression as well. And in the software of the DVS analysis, we also have the option to exclude some of the points. For example, if you think this point is not inside the linear line, you can also exclude this point from the calculation, and then you can get an even linear R square for the BET plot. So this is the application related to the BET calculation. And the next application I would like to introduce is about the formation of hydrate. So basically, it's an uptake at certain step that is for the formation of hydrate for pharmaceutical material. So here we have the sample. We perform the sorption experiment as the step method we introduced previously. And this sample is pretty much stable below 40% RH, almost around 0.3 uptake. And then at this single step, it can pick up lots of water. And this is because of the formation of the hydrate. And the sample can, during the desorption step, is losing the water and go back to the 0 point. And in the second cycle, it's the same level as the first cycle sorption. So this is a kind of reversible hydrate formation for the sample. And when you plot the isotherm, you can get this typical isotherm for the hydrate formation that at single step, you have an uptake of the water. And if you have the molecular weight of the sample beginning with, you can then calculate how much water is hydrated inside the material. It's forming a monohydrate or dihydrate or trihydrate from the shape of this isotherm or the uptake at a certain stage. So this is a kind of reversible hydrate formation. We also have an example here about the irreversible hydrate formation. So we also do the 2 cycle of moisture sorption desorption on the sample. So the right line is for the sorption on the first cycle. Blue line is for the desorption for the first cycle, and the pink and green line for the second cycle. So this time, during the second cycle, it's not the same level as the first cycle anymore. So it's not overlapping with the first cycle. So the sample already changed the nature of the material at the end of first cycle. It's not the same nature of the sample anymore compared to the original sample. And that is because of the irreversible hydrate formation during the sample. So I think the last application I'd like to show here is about the batch-to-batch variation. So DBS balance is a quite sensitive balance with the resolution of 0.1 microgram, and we can detect really small surface sorption differences from the mass uptake. So basically here, the uptake of the sample is only about 0.7 or less than 0.1. And there are still some difference between the sample. And this difference could be related to the batch-to-batch variation between different samples. And that's the hydrophobic drug. So normally, if the moisture sorption is above 1% mass change, we can say it's a kind of bulk sorption dominating mechanism. And if it's below 1% mass change, it's basically a surface sorption that most of the water molecule just condensation on the surface with very low uptake. And I think that's probably all for my applications. This presentation just related to the applications for the pharmaceutical ingredients and how we measure the moisture content from the item of the DVS data. And I hope you can find DVS very useful in your future research. And at the end, if you have any more questions or if you want to know more about the sorption science, I just want to give you some information about we do have a online symposium happening at the end of this month, and you are more than welcome to join our symposium online. And please let me know if you have any questions, and thank you very much for your listening. Thank you.
Thank you, Mei Shan. And yes, just a reminder to our audience, we'll now have any questions for the speaker. To submit these, you can either submit them in writing in the questions panel, or you can raise your hand and I will let you know when you can unmute to ask your question. So just a few questions we have here submitted already. Let me just pull those up. Mei Shan, someone has asked, how do they use Raman with dynamic vapor absorption?
Okay. So maybe can I share the screen again?
Yeah, sure. I'll make you the presenter.
Okay, that's great. So basically, we have stand. We showed the instrument before. Yes, you may have. You can see here that there is a brass top on the top of the sample chamber, and that's the port for the Raman gun. So we have the Raman spectra, and we have a port for the Raman gun. You just put the Raman gun inside, and the software will automatically trigger the collection of the Raman spectra at the end of each humidity step. We do have the software already integrated with the Raman software. But if you have your own Raman software or your own Raman spectroscopimeter, and maybe you can also do it manually as well. And aside from the Raman, we can also collect or integrate it with IR spectrometer as well. And as long as the sample is Raman active, then we can perform the Raman with the DVS.
Brilliant, thank you. Our next question is, how does dynamic vapor absorption for amorphous content determination compare with other traditional methods?
Okay, thank you for your question. So we do have quite a lot of publications related to the amorphous content determination with DVS technique, and some of the papers comparing between the traditional method with DVS method, and they found out that it's more sensitive, especially for some low amorphous content material, like below 10%. And as DVS method is quite active, sensitive in this way, it can give a really good reproducibility for different runs. So if you're interested in the amorphous content determination, we are very happy to share the publication with you after the meeting.
Thank you. We have a question here from Zaid Asaf. And first he says, great presentation. And his question is, how universal is the BET method by Octane? And he has given a comment here saying, a fundamental assumption of the BET equation is that all surface sites are energetically equivalent. Nitrogen gas is chosen because it can interact with dispersion forces, which are uniform and are small in size. Octane is much larger and not as uniform in dispersion interactions. So how would octane BET apply in a heterogeneous material like activated carbon?
So basically, we compare some of the commercial sample before, like active carbon or carbon black, and we do get very similar results compared to the nitrogen sorption technique. And you may think octane molecule is a bit larger, but in the ISO standard for the BET determination, octane or some other organic vapor is written as a pro molecule as a standard for the determination of BET as well. And those organic vapor can be used at ambient temperature, and the nitrogen molecule can only be used at liquid nitrogen temperature. So one of the big difference between the two techniques is the condition to perform the experiment. Liquid nitrogen temperature has some extreme conditions and also degassing with the vacuum, and those can empty some of the pores. So in that case, you may measure a bit smaller surface area compared to the surface nitrogen sorption technique. But in the other cases, most of the samples, we do have very comparable sample results with the nitrogen sorption. And especially for some low surface area material, DBS method is more sensitive, and nitrogen sorption, in that case, you may need to use some some other pro molecule like krypton to get some more accurate results.
Thank you. We hope that answered your question, Zaid. And another question here, can you do gas sorption with the DVS method?
So with the instrument I introducing today for resolution, there are all the flow system with the carrier gas, which is nitrogen or air. This instrument cannot do the gas sorption, but we do have a vacuum system that use the vacuum pump and only the measure the sorption of the molecules by pressure. And in that case, we can do any kind of gas sorption like CO2 sorption, SO2 sorption, or hydrogen sorption. So if you're interested in the gas sorption, we can also have another kind of material for you, just giving you more information about our vacuum system.
Brilliant. Thank you, Meishan.
Thank
I
you.
think that is all the questions we have for today. So thank you once again, Meishan, for a fantastic presentation.
Thank you for your listening.
Thank you, everyone. Now, before we leave, I would like to take the opportunity to invite you all to, as Meishan mentioned, our upcoming Sorption Science Symposium 2021. This is our second European Sorption Science Symposium, and this is the first virtual edition, taking place online on the 22nd and 23rd of September. As pharma is such a big part of the DVS applications and the IGC applications, we will have a full morning of the agenda will be dedicated solely to pharma, with the rest of the agenda also being dedicated to sorption science and IGC and DVS. So it's a fantastic learning opportunity for any researchers or scientists involved in the pharma market and pharma research. We will have, as well as the morning of dedicated pharma sessions with live Q&As with the speakers, you will also be able to engage in a pharma video networking session. And this session will also be complemented by all the other networking functions and tools we'll have at the event. And these will include live video lounges for sharing and discussing content, attendee matchmaking, networking events, and live and group chat throughout the event. So it's a great opportunity. And for any of you, while the event is taking place in the European time zone, the sessions will all be on demand, and the poster sessions are all on demand, so you can attend from anywhere in the world. And what's a really great benefit is that all of the chat rooms, whether it's a session chat room, a Q&A room, a group chat, any of that is available throughout the event wherever you are. So you can check in any time of the day, check back on the message for any useful insights or discussion, and add your thoughts to the discussion. And as attendees at today's webinar, we would like to offer you an exclusive discount of 50% on the cost of your ticket. So a full price ticket would only cost you £35. And to claim this, simply use the code WEB2097 when registering. And the website address is at the bottom of the slide there. You will also get these details in an email after the event. So you are all invited to attend the event and get up to date on your pharma, IGC and DVS knowledge. Just to add to that, there will also be all of the SMS team present at the event. So if you have any detailed queries or perhaps would like some advice on a particular experiment or piece of research you're conducting, we'll be there to discuss that with you face to face, or well, as face to face as we can get in an online event, excuse me. So once again, we hope to see you all there in 2 weeks, and thank you again for attending today's session. Have a wonderful morning, afternoon, or evening, wherever you are. Thank you.